Okay, hello and welcome to part 4 in this video series where we're looking at the June 2013 mechanics paper. So moving on to question 4, which shows a metal ball held stationary above a tube containing oil. The ball is 0.7 meters above the surface of the oil in the tube. Calculate the time taken for the ball to reach the surface of the oil when it's dropped from this height. And it's just telling you to ignore air resistance. Okay, hopefully you can tell that you'll need an equation of motion to find the answer for the time, and so you need to select the correct one from your formula book. How do you go about doing that? Well, an easy way to do it is to write down all of the variables that appear in all of those equations. So we've got A, which is the acceleration, we've got U, the initial velocity, V, the final velocity, S, the distance, and T, the time. And what I do is I write down everything you know from this question, and then it'll become obvious which one you select. So do we have any information about acceleration? Definitely, because it's an object in free fall, so that's 9.81 meters per second squared. Initial velocity, well, if it's dropped from this height, that's going to be 0. We don't have any information about the final velocity. The distance, which is the height, 0.7 meters, and the time is what we want, so that's what the question's asking for. So we need to find an equation of motion that has A, U, S, and T. Okay, so if you look at your formula booklet, you should have S equals UT plus half AT squared. Okay, so if I underneath this part A here, I'll just go through how you work out T. If we just start off by recognizing that because U 0, UT, this first term is going to drop out. So step 1, we're just going to have S equals half AT squared. Okay, step 2, I'll just solve for T squared, which means the 2 goes up the top, so that's 2S over A. Okay, and then moving on to step 3 over here, I'll just start plugging in some numbers. So T squared equals 2 times S, which is 0.7. Okay, and that's going to be over 9.81. Okay, finally I just need to square root both sides. So T is going to be equal to 1.4 over 9.81. If you plug that into your calculator, you'll get an answer of 0.38 seconds. Okay, so the important thing to recognise here is that it requires an equation of motion. If you write the variables out and the information you have for the variables, it'll become obvious which one you need to select, and then you just work it through. Okay, so next question. Okay, so this is showing you the graph of velocity against time for the ball as it travels through the oil. Okay, so the first question says complete the sentence below. The gradient of the graph is equal to the, well, if you remember back from GCSE, a velocity time graph, the gradient is acceleration, but in this case it's more specifically it's a deceleration. It's going through the oil and it's slowing down. And the area under the graph, again this is GCSE stuff, area underneath the velocity time graph gives you distance. Okay, so that's a nice easy question, that one. So the next part, use figure 4.2 to determine the magnitude of the deceleration of the ball at t equals 0.05 seconds, which is point A. Show your working. Well, we know the deceleration is the gradient of the graph. The problem is the gradient is constantly changing down here. So to work out the gradient at point A, if you remember from class, you need to take the tangent at point A and calculate the gradient of that tangent. Okay, so hopefully I can try and show you this on the graph. So obviously a tangent is a point that just a tangent is a line that just touches the point A here. Okay, if I selected another colour, what I need to do next is draw a triangle so I can work out the gradient of this tangent I've just drawn. Okay, so now if I start writing the values I've got, so I've got this point at the top here, so if I read off there, that's 2.2, so 2.2. If I read off this point here, that's 1.4. This point here, if I read down to here, every 2 squares is 0.01, so 0.01, 0.025, so that's 0.025. 0.25. Then this point I've got down here, if I read all the way down to there, I've got 0.1. So if I go backwards, 0.09, 0.08. Well, it's down here, 0.08. Okay, so now all I've got to do is I've got to write what the gradient is. So m equals the change in y, because m is the gradient of this tangent, over change in x. Okay, then I'll write my change in y. So I've got 2.2, take away 1.4. Okay, so I've got 0.8. Okay, over, now I've got 0.08 minus 0.025. Okay, so that's going to be 0.055. Okay, so then I'll just work that out. So I've got 0.8, and then I've got to take 0.055, gives me 14.5. So 14.5. So deceleration, so it's going to be in meters per second squared. Okay, obviously I've got this on separate slides, so I've done the working to the side of the graph, but you'll obviously do it underneath here. So that's 14.5 meters per second squared. Okay, the mark scheme is giving a range of 13 to 17. So if you get a gradient that's less than 13 or greater than 17, you won't get the mark. That just means you haven't quite drawn your tangent right. Okay, so moving on to the next part. In terms of the forces acting on the ball, describe and explain the motion when t equals 0.05 seconds. So that's point A. So in terms of the forces, describe and explain the motion. So we need to know what the forces are and what the motion is at point A. Okay, so point A on the graph's here. Well, the forces, obviously, if it's travelling through a liquid, there's going to be resistive forces. Okay, because the liquid it's travelling through, we call those drag forces. And there's also obviously going to be the weight force acting downwards. So those are the two forces. We need to use those to explain the motion. Well, the motion is at point A, it's decelerating. So how can we use those forces to explain that? Well, if something's decelerating, that must mean that the drag force, which is this opposing force, must be greater than the weight force. Okay, so we need to put drag force is greater than the weight force. Okay, that'll give you 1 mark. So object is decelerating, or you could say slowing down. We'll get you the other mark. Okay, so we apply the same thing again, but just describe the motion at point B this time. Okay, so let's just go back to point B. What's happening at point B? Well, at point B, you can clearly see that it's reached its terminal velocity. It's probably reached its terminal velocity about here on the graph. Okay, so no longer is there there's no decrease in velocity anymore. It's reached its terminal velocity. So that means it's not slowing up. Sorry, it's not speeding up or slowing down. Therefore, the net force must be 0. Because if the net force is 0 on an object, it doesn't speed up, it doesn't slow down. There's no acceleration. And if the only force is a drag and weight force, and there's no net force, that must mean the drag force equals the weight force. So we need to put drag force is equal to the weight force. Okay, you can say object has reached terminal velocity. Okay, so that'll get you 1 mark, and this will get you the other mark. Okay, so final part, describe the energy transfers taking place between points B and C. Energy transfers. So let's go back to the graph again. So between points B and C, what are the energy transfers that are taking place? Okay, we've got to recognize what the energy has started off with. So if I go back to the graph here, okay, this energy is obviously going to be gravitational potential energy it starts with. Let's try and work through what happens to that gravitational potential energy, because when it hits the bottom of the tube, it's a gravitational potential energy is going to equal 0. So obviously it's being transferred to different kinds of energy on its way down. We've got to figure out what that is between points B and C. Well, if we just go for the first initial part, where it goes from here to the top of the oil, Okay, it does say in the question, assume air resistance is negligible. Therefore, if we assume, basically it's saying ignore air resistance. So the gravitational potential energy between this point and this point will all go into kinetic energy. Okay, but there's still gravitational potential energy left. Okay, so what happens to it from when it travels through the oil? Okay, when it travels through the oil, if you look at the graph, there is no increase in kinetic energy anymore. So none of the gravitational potential energy from here can go into kinetic energy. So it's got to go in some other form of energy. Okay, because you can see from the graph, not only does the kinetic energy not increase, but it actually decreases as it goes through the oil. Okay, so we've got to try and understand what's going on here. So um, for the velocity to decrease, that means the kinetic energy is decreasing. So actually, where's all this energy going? Because the kinetic energy is decreasing and gravitational potential energy is not going into kinetic energy. So where's all this energy going? Well, obviously, if you've got this resistive drag force. So when the ball hits the oil and it goes through the oil, okay, it has to force its way through the oil, and there's obviously molecules of oil getting in the way, causing friction and so forth. So the energy will therefore go into heat caused by the friction as the ball is trying to force its way through the oil. Okay, so from the point when it hits the oil to the point where it's reached its terminal velocity, gravitational potential energy is going into heat, or thermal energy is probably a better word, and also the kinetic energy that it had just before it hit the oil, some of that is also going into heat. Okay, but it is asking specifically what's happening between points B and C. Well, if the kinetic energy is the same because it's reached terminal velocity, there's no longer any kinetic energy going into thermal energy, but it still hasn't reached the bottom yet, so there definitely will still be gravitational potential energy going into thermal energy. Okay, so I kind of gave you that as a bit of extra information, the fact that obviously some of the kinetic energy it had as it hit the surface of the oil also has to go into thermal energy. But the point to recognise is that from the point when it hits the oil to the point at the bottom, that gravitational potential energy, none of it's going into kinetic energy. So therefore it has to go into another form of energy, which is the thermal energy, as it's kind of forcing its way through these oil molecules. So all we need to put for this final bit is that gravitational potential energy, I'm just going to abbreviate it, okay, is converted into thermal energy. Okay, and that'll get you the marks for that last part. So I'm going to stop the video there, and then in part 5 I'll go through the next part.